everyone. It's a pleasure to welcome you to this panel discussion at SSGS Innovation in the Value Chain Business and Technology Focus. My name is Irina Petrova, and I'm the VP of Marcom and Membership at GSAR. If there's someone in the room who doesn't know who GSAR is, we are the leading global CEO-driven association representing satellite operators across GEO, MEO, LEO orbits, as well as manufacturers, launch providers, ground segment companies, and other key players in the satellite ecosystem. We are the premier platform for industry collaboration, tackling global challenges, advancing regional opportunities, and advocating with a unified voice for a more innovative and reliable satellite sector. As the space sector continues to grow, rapidly driven by technological breakthroughs, expanding commercial applications, and increasing global demand for connectivity, security, and sustainability, the value chain supporting it is undergoing a transformation that one of its own. Innovation today is not just about technologies. It's about how we design, manufacture, collaborate across borders and sectors, and how we fund and scale new ideas, and how we ensure that each part of the value chain contributes to the real-world impact, economically, socially, and strategically. Our discussion today will focus on innovation involving in different points of this value chain, from components and subsystems to system integration, services, and different business models, and what it means for the competitiveness of the UK and European space industry in the years ahead. We are fortunate enough to be joined by some of the key leaders in this sector and innovators in this space who bring rich experience from both technological and the commercial sides of the sector. So before we begin our discussion, I would like to invite each panelist to give us a short presentation, sharing their perspective on how they see this product. So first, I would like to welcome Malachy Devlin, CEO of the Celestia UK. Malachy, if you would take the stage, please. Celestia is known for its work in ground segment technologies and enabling secure, high-performance communications infrastructure for the space sector. So let's have a look at the presentation and tell us to move if you can't see it.
Okay, thanks very much for the introduction. And good to have everybody here. So talking about Celestia, Miguel was up earlier, so he did give a brief introduction to Celestia, but I've got some pictures to go with what he was saying earlier. So Celestia, we've been around almost 30 years, so obviously been involved in quite a wide range of things in the ground segment, so covering things from SSPAs, LNAs, sort of standard temperature. We also do cryogenic LNAs, which get used in some of the deep space telescopes, right through to ground systems, the modems in behind there as well, and also phased array technology as well. So on that front, we've been doing that for quite a while, sort of all frequencies going from L-band, S-band, right through, and I'll talk a wee bit more about what we're doing on Ka-band. Some of the other areas that we're working in, and it's interesting, a few of these has been mentioned as well during the course of today. So looking at lunar comms. So while it seems lunar, we do need a ground segment for that as well. Also, optical comms is becoming an interesting topic, so we do some modems and that side of things. And also the space surveillance, just being able to, it's getting busy up there, so how do we actually keep an eye on what's going on? Because sometimes you have to assume that you don't always get the true telemetry of some of the assets that's in orbit. As a company, we're pan-European, so I think we've got most countries covered there. So these are kind of our main offices around Spain, France, Netherlands, Belgium, UK here as well. And so one of the things just to kind of focus on, just because we're looking at innovation, is something that we are working on, and this has been driven with as we know, there's a lot of satellites going up there, so the number keeps increasing, and we are putting up thousands, and I think it was mentioned earlier, there's probably too rich people that are doing a lot of that, but equally there is other organizations are bringing up constellations, but not necessarily the size of tens of thousands, but certainly those kind of in the tens and the hundreds side of things. So it's certainly a lot more growth going on there. Now, there's also got mentioned as well about bandwidth. So what's interesting, where we started off with, UHF, VHF, S-band, X-band, etc. We're going to K-band. We just keep going up the alphabet here. But while we're putting up more satellites, we are also increasing the frequencies as well, which is actually accelerating. So while the growth of satellites is interesting, the growth of bandwidth's getting bigger as well, just as a consequence of going up in frequency. And then also this trend of going from GEO down to LEO. Because it's closer to the Earth, it doesn't actually have as much visibility of the Earth as well. So for it to be able to contact with something, it's a smaller area, so you'll need sort of more points of contact on the ground as well. So again, it's another accelerator on the ground side. So I guess for everybody in the room involved in the ground segment, that's probably a good thing to hear. So that's some of the drivers. Now, how we, sorry, there's my little graph showing how that's been scaling up relatively recently. Now, ground segment, this is certainly for a teleport. This is a real-world example. And the way we solve it, parabolic dishes, that's been our typical way of addressing that. Now, as you can see here, there takes up a lot of space. I think actually it was interesting, Andy was talking about earlier about, they have the site and they need to have the security and, being able to have it, if it's remote, being able to have it sort of run when it loses power, etc. So this is the typical solution. Now, we've, while we do parabolic, work with parabolic systems, we also do phased arrays as well. So a very non-technical explanation of phased arrays, because I know some people will understand it, but others is probably, there's a lot of technology behind it. But if you look in nature, the chameleon can sort of give you a full field of view. They do that by, as you can see, using the eyes. So it's like, think of that as your parabolic dish. We can scan the sky and look or talk to any part of the sky. Whereas if we look at the fly here, it's got a compound eye, which is actually made up of a whole array of smaller little eyes, if you like. Each one's got its own optical lens, and it can, again, still see that visibility with nothing actually moves in that case. So it's the simplest example I can give of the difference between a mechanical dish and a phased array for anybody that doesn't understand that. So what we were looking at is, could they be used to look at the ground segment? Because if we're getting a scale up on satellites, how do we scale up the ground segment apart from buying more land, putting out more and more dishes? So this is something we've been looking at. So it's really on the left-hand side, there's your mechanical dishes. On the right-hand side, this is the kind of punchline of sort of what we've been working on, and doing phased arrays, because what we have to do, it's different to what you have as a Starlink. We see sort of examples where people are using flat panel antennas, which is on the user terminal. So, if you're wanting that sort of 100 megabits of bandwidth, absolutely loads of solutions in there, and it's not something we're trying to address. What we're trying to look at is the feeder links is really what we're trying to address. So when I talk about Ka band, it's not a channel in Ka band. I need to address the full band simultaneously, which is, that in itself is a kind of a challenge to do as well. So that's, we wanted to understand, can we do that? And also, can we give the same coverage on the sky as well using phased arrays? And obviously, being in business, can you make that commercially viable as well? So rather than a pure research project. So the answer is, this is what we've been working at. And so giving you sort of an idea, moving from one to the other. And some of the other consequences of being able to reduce this down to a more compact size is that all of a sudden, instead of having a large field and just putting it in the corner of a field, well, why are we putting it in the field now? So we can actually bring it closer to where we have the data centers, and we talk about latency, so you can pull some of that out. There's security infrastructure as well. So I flippantly do say you drill a hole in the roof and plug it in. There's probably a little bit more to it than that. So there's just consequences of just changing the form factor as well, that when you're architecture and your overall system and network. And so from a scalability and moving forward, it does give other options of what you can do. Yeah, and the other thing is it's electronic. It's effectively solid state. There's nothing moves, so it's software controls this. So I can change beams. I can change the shape of them to if there's interference in one direction and everything. So there's a lot more flexibility that we have there. And because it's electronic, nothing moves. For me to point to any part of the sky, I have no penalty. I can go from one side of the sky to the other side of the sky with the same time as it takes me just to track a satellite itself. So this is the system that we're been building. So trying to give you a sort of a gauge of the size. That's why we put it in shipping containers. It's kind of a known size. Everybody knows the size of that. And here are some of the advantages that we have from a technical perspective. Now, in terms of the status, phased arrays have been talked about for years, and there's been good and bad results of that. Like to sort of say we've had a positive result last year. So we've actually built this here. This is a demonstration done in the UK. It's up in Dundee, up in Scotland. And so we've been fortuitous. We're working with OneWeb, or Eutelsat, I think the branding's got it now. So we have that tested with actual spacecraft, so that sort of assures that we can actually track satellites, shape the beams and everything to do all that. So we're doing a testing. It's been going on over 9 months, range of orbits in there as well that we've been doing that across as well. And we've done a lot of technical confirmations, and that's been observed with ESA, who are usually pretty stringent in their observations when you're doing a review, and obviously with OneWeb as well. And we've moved on from that, and we're now actually building a much larger system now, and that's in the works. Okay, hopefully that was my 10 minutes. Okay, thank you.
Next, we'll hear from Dr. Tudor Williams, CTO of Filtronic. Filtronic has been at the forefront of advanced RF solutions, providing critical components for satellite communications, aerospace, and defense. Tudor?
Thank you very much. Lovely, thanks. Good afternoon, everyone. So I'm Tudor, as I said. So I'm going to talk to you a little bit about what Filtronic are doing in this market. I guess we're maybe a little unknown in the market. We're fairly new to this game. But what we've been doing really is transforming our business based on the new space model. So these mega constellations, people wanting lower cost but high performance RF goods, and we have a massive background in RF. We tend to specialize on the higher millimeter wave spectrum, like the last presenter was talking about. Ka-band is becoming more prevalent. We're actually working at much higher frequencies. We're doing QV band, we're doing E band, and even W band for SATCOMs. But you can see the results there. So the last couple of years, we've seen massive growth, over doubled our revenue last year to 55 million, and massive growth in the engineering team behind that as well. So we've taken on 50 engineers in the last 12 months to support that growth in the business. And we're just about to move into a new facility, which is twice the size and 6 tons of manufacturing space to scale that business even further, based on the opportunities we see. So it builds on 45 years of experience. We've been around since the 70s. Most of our work in the past has been in the comms business. So we did a lot of work in, for example, mobile backhaul, so point-to-point links. And as this market started to emerge, the sort of the volume space market, if you like, people started approaching us and saying, could we help them to do space-to-ground links, space-to-space links? And we sort of pivoted into that business, and we've seen real benefits in doing that. Now I have to wait for the animation. I hate animated slides. But that's where we focus. So we focus on SSPAs, LNAs, frequency converters, transceivers, bucks and LNBs, TRMs for phased arrays, and also custom filters. As the name suggests, Filtronics. That's where we started in the 70s, doing airborne filters for airborne platforms. And from that, we've developed a whole microwave capability. But we can do anything in the RF front end, basically anything from the modem right through to the antenna. And we're completely vertically integrated. So we have anything from chip designs. We do our own chip designs. We do our own design. We do our own manufacture. And we do our own test and measurement as well, all within the north of England in the UK. So completely vertically integrated. There's the bit we focus on. So anything Ka above, really. So Ka band, QV band, E band, W-band, and then in the future, probably D-band, but that's probably some years away yet for requirement. So I'm going to talk about one particular use case, I guess, and I'm going to talk about the SSPAs, which is where we've had the most success at present. We develop very high-frequency modules that will compete with TWTs, which is the incumbent technology. In millimeter wave frequencies, people tend to have to use TWTAs because they produce higher powers. We're trying to come at that from a different angle and look at solid-state alternatives. So we've moved to materials like gallium nitride and then combining networks that allow us to compete in terms of power level with those TWTs and trying to overcome some of the disadvantages, which, and the complexity of a build of a TWT. They're quite complex to build. They take quite a long time to do that, which means they typically have a very long lead time. They've got a limited lifespan within the system as well, so they tend to have to be replaced every 5 to 7 years. And they do tend to degrade over time. So we're trying to compete with that, and obviously on cost as well. So we're trying to compete on cost. So what kind of innovation was required there? We needed cutting-edge semiconductor technology nodes, so we need to move to the latest technologies. And these GaN processes, these gallium nitride processes that allow us to get these sort of power levels are pretty new. The node sizes have shrunk down now enough to support E-band and V-band sort of designs. That's fairly new. So we're right at the cutting edge of that technology, and all the problems that includes, including having to work out how the process works, how to model it, how to get the best out of the devices. I mentioned combining. I'll show you a bit on the next slide what that looks like. But we have to have very low loss combining structures because each device will only give a few watts of power, and we're trying to scale this to hundreds of watts of power, ideally, in designs. Alongside that, because of the frequencies involved, so if we're working at 80 gigahertz, the manufacturing techniques and tolerances are very, very low. You have to work very hard to do good design work at that frequency, but also to manufacture, particularly in volume, when you have to scale volume to hundreds of amplifiers, for example, per week. That's quite hard to do, but we're managing to do that. Process engineering covers everything from sort of die attach, wire bonding. Again, very high precision required at these very high frequencies, and quite a good capability there. And then, probably most important is cost engineering. How do we make these things really cost effective, and what design approach do we take to make them cost effective? I think that's where, as you said, it's not just the innovation in technical terms, but it's the cost as well. How do we drive the cost out of these things? How do we do design that's competitive on cost? So there's one of our amplifiers. I don't know if there's a pointer, but in the middle there, one of our amplifiers there. It actually has 32 little mimics on there, so 32 individual PA devices. So we take the signal, we split it 32 ways, we run it through all the amplifiers, and then we recombine back together. And that gives a V-band 100 watts of output power. At E-band, 81 to 86, that gives about 20 watts of output power, based on gallium arsenide. And we have a GaN version of that coming as well, which will give you 50 watts of output power at 81 to 86. So quite high powers, really, and world-leading power levels. So very clever design in there in terms of splitting and combining. And it's all done within the actual metal block that you see. So that's all waveguide. It's all milled out in waveguide with very, very fine tolerances. And what we found in terms of sort of partnerships is supply chain partners are important too. You have to work with your suppliers to actually let them develop techniques that will let you do that, again, at cost. So they can do it with the very highest precision machines, but if you work with them, there's often ways around that to actually drop the cost and drive the volume up. I mentioned the chipset, and we do our own custom designs on chipsets. Using the cutting-edge technology is really important, finding the best processes. And when you start that's quite expensive. So if you want to design a chip, you have all your engineering wafer runs, and then production lots. It can take anywhere between £300,000 and £500,000 to develop a chipset at each frequency. And typically you want to do it on more than one fab as well, because there's multiple options in fabs, all give different performance. So there's a lot of cost in there, and a lot of technology and design work in there. Some of the other problems we solved in this is sort of thermal challenges. So one of the things with solid state is it's not quite as efficient as TWTs, so you have to get a lot of heat out of these things. That comes down to lots of different things, thermal modeling, for example, but also then the process engineering, how you stick that die down. That interface between the die and the rest of the world is really critical. Any heat that gets held up in the die just kills performance. And then I talked already about the precision manufacturing and high tolerance repeatability. And then that supply chain innovation, that's working with the people doing the metal work. It's working with people doing PCBs that let you use cheaper and more cost-effective materials, but processing that in a different way. So, for example, we use softboard, which is quite a cheap PCB material, but we're doing frequencies up to 81 gigahertz, which would typically be done with the exotic substrate, like some sort of Rogers substrate. So that's what we get in the end. We get very high reliability, long lifespan. There's built-in redundancy. That's another big differentiator between a TWT and an SSPA, particularly in this sort of format where we have 32 devices. If we lose one device, you lose a fraction of the power. Basically, you don't lose the whole link. You use a tiny amount of power. Short production time, so we can turn around these things in probably 8 weeks, 8-week lead times, and we're producing thousands of these a year for different customers. And obviously lower cost. And there's the sort of performance we get, as I said, V-band, 100 watts, 20 watts at E-band. And they're sort of state-of-the-art. There's no one else producing SSPAs at that sort of power level. How am I doing for time? Over. I will quickly go through and I'll do one last slide. So one of the big things we have that is a collaboration with SpaceX. We're now a strategic partner with SpaceX, and we've been delivering E-band SSPAs for their ground network for over a year now. That's quite applauded, I think. They do everything themselves if they can, and I think this is the one thing they can't do. This very high frequency electronics is difficult to do in terms of design, but also manufacture, and also scaling up the volume is difficult. And that's really been transformational. You can see the nice words that SpaceX have given us there. The ability to actually work with them and work quickly enough for them is really difficult. And as an engineering company, we've managed to do that, so we stayed ahead of that. We took this actually from concept through to full design and production in 6 months for SpaceX, so we did a good job of ramping that as an Agile sort of SME. And I'll stop talking now because I'm obviously over time.
Thank you. And lastly, let's hear from Obilor Nwamadi, a Senior Product Manager at VIAVI Solutions. VIAVI may be a new name for some of you, so please. But they play a key role in enabling advanced testing and assurances across satellite and telecom networks. Obi would love to hear more about VIAVI, because I'm sure a few people in the room have not heard that name before.
Yes. Hi, everyone. My name is Obilor Nwamadi, and everybody calls me Obi. And before you go there, yes, the joke isn't lost on me. Yeah, somebody with the name Obi working in satellite and space industry. So I have about 10 minutes, and I'll try and do my best to go as fast as possible and add some technical nuggets in there as well. So VIAVI, who are we? My division is based just outside London in Stevenage, where some of the large companies such as Airbus, GSK are based. And we have 2 major divisions. There's the NSE on the left, and the optical and security part on the right. So the NSE is what I'll be focusing on today. That's where we do the wireless, and that's where we also do things like fiber connections and things like that. On the right-hand side as well, NTN has gone into that bit, as a lot of talk about optical this morning. So the team there, the OSP team there, in addition to making sensors for phones and making ink for money, also make filters that you can use for ISILs, so inter-satellite links as well. So NTN has cut across the whole company. And the wireless business unit. So most people have not heard of VIAVI maybe, but many people have heard of Marconi Instruments. So that is the historical name and company behind VIAVI. And over the years, it has bought up many companies, Rayco, Ubinetic, Shenik in Ireland. And the wireless business unit is headquartered in Stevenage, like I said, and we do a lot of the development there for both the 3G, 4G, 5G, and now 6G research, as well as NTN. So VIAVI as a whole, the NTN, like I said, is cutting across the whole business. So I'll just touch on a few. You can see the PNT solutions there, so position, timing, and navigation for secure and resilient timing when your GNSS is jammed. And then the FSO is your free space optics, and that's what we've been talking about a lot today. And then bottom there as well, focus on where we have testing solutions for UE emulation and core emulation for testing your RAN. So yes, the whole, till now, nobody has spoken about testing. And it's interesting, right? We're spending a lot of money building all these very complex systems. How do you make sure it works before deploying, right? Especially with NTN. You want to make sure it's doing the job before you deploy it. So this is like a breakdown of 3GPP NTN using the transparent architecture. So you can see on the left-hand side there, you can have new codecs. So some people are actively working in that area to reduce the amount of data you need to send. The cost per bit over satellite is expensive. You want to make it as efficient as possible. And then that's where we come in the next one there. That is the UE emulator, the TM500, that has over 20-year pedigree. Like I said, had the WCDMA implementation, had a 4G implementation, has a 5G implementation, and we're already working on the 6G implementation now. And you can use that as your 3GPP stack, right? So till date, we have IoT chipsets in the market for NTN, really 17. But the NR chipsets are not yet in the market, right? How are people testing this before deploying? One is to use the VIAVI product there, not just as a test equipment, but actually as a stand-in for the chipset, for the stack, before you get to that point, right? And then the next item there on that list is your antennas. A lot of talk about antennas today. Now, this is for the UE side. When you have NTN on a handset, direct-to-device, direct-to-cell, the link budget becomes very important. Many people are working on some new antennas that could change or update the antenna structures on phones so that you can make that link budget effective. And then you have the payload systems up there, which everybody knows about, building the satellites and taking it up and launching into space. And then the topic for this whole conference, the ground systems. 3GPP, with this architecture, makes the ground systems a bit more complex now. So if you have the next item just after the gateway is your RAN. And your RAN can be split up as well, right? So ORAN, you can have your PHY, you can have your DU, and you can have your CU. And in the beauty of 3GPP, this is just one option of having your RAN sit behind your gateway, in between your gateway and your core, right? So ground segment now will include aspects of the RAN, the G node B or the E node B. So that needs to be factored in to ground segment design, right? And then your core as well. We have heard today hyperscalers coming in, bringing core on cloud. Now that is part of the ground system as a whole, with the RAN in there. The next option, just before we go to the next option, like I said before, TM500 acting as a stand-in, many people have used it to test their geo satellites already. So on the left-hand side was SUTD with JSAT, doing it at the Soccer Expo. Kratos, Intelsat doing it in US, and then KTSat doing it in Korea as well. So the task here was to take the TM500, use it as a modem, put it through an antenna, either a parabolic or an ESA, and send the 5G waveform to their existing satellites to make sure that the satellites that supported DVB will also support the 5G waveform. And these geo satellites will reflect that same waveform down towards the gateway as well. And so that was a whole challenge, making sure you close the link budget over geo, and the Osaka Expo actually transmitted a live video call using a system like this. Okay, the next one is regenerative. I'll go a bit faster. You see the complexity here is the RAN can be deployed on the satellite. And I split it up again there. You could have your PHY, you could have your DU and your CU all on the satellite. Or one of the options is that the CU could drop down and go behind the gateway. And all of a sudden, you have your DU and your CU split over a feeder link. Now, ground systems need to adapt to that. That will be the F1 interface, which is typically run over fiber now having to be transported over a satellite radio interface, right? Are the ground systems ready for that kind of challenge? Many people are thinking of building it like this. The other option is to put the DU and the CU behind the gateway and leave the L15RU at the top on the satellite. Now, that is your O-RAN front haul interface split over a satellite radio interface. That, as well, even the O-RAN Alliance hasn't updated their spec to handle that type, right? The latencies there are beyond anything that is defined in any spec as we speak, right? So ground systems need to evolve, especially with the different ways people are thinking of building these. And I have seen it out there in the field. Everybody has their own plan, slightly different. So the discussion this morning about having a unified ground system framework, now, the split matters, right? You don't get the split right, and then you have different systems you have to manage, right? And then there's ISOs as well. When you have regenerative, then satellites can speak to each other over a fiber link, and that's the one that we've spoken about a lot. And then with the fiber link going down to the gateway as well today. So many options and many things to innovate on. And VIAVI's task, at least my division, is to see where the innovation is and see how do we test that. Because the aim is to test early, test faster, and in the words of some people, fail fast. You don't want to invest a lot of money like Malachy has done and then find a satellite operator to try it out and see that it doesn't work. You want to do all that early in your cycle, right? The other thing there for innovation is non-3GPP access. So non-3GPP access is what we have now, and it's not going away, it wouldn't go away tomorrow. So how do you interface non-3GPP satellite access with NTN? The N3IWF is there to do that. That's an interface, and that's 10 minutes. I timed myself. Okay, so I'll go faster and finish it. So yes, so innovation for the N3IWF is essential so that you can have the current systems work with the new systems that are coming up as well. All right, so how do we do this now? We can test the whole system on the test in the middle, everything in green, by having interfaces, UE on one side, satellite channel emulator on one side, and then the core on the other side. But you can see that the gateway itself is not tested by itself. So you could go in there, get an interface, and have a core emulator instead, and then you bracket test the gateway, right? You want to test early, you want to test fast. All right, and the final thing, I know you're going to ask me about this, is how do you even test earlier modeling, right? Doing everything even before you get to RF. And this is where things like AI and emulation, simulation will play a big part here. And this is what we call this RAN scenario generator that incorporates both satellite and terrestrial networks, and you merge them together, you have a big model, and then you see what your system is like before you actually deploy and design it. Cool. Thank you. How many? Yes.
Well, that was exactly one of the questions that I wanted to touch upon. But we may continue this conversation, so I can just then ask you, how are you leveraging these technologies in practice? Because now you mentioned this AI, ML, digital twins. So what do you actually do with them in practice? And to which extent some standards would help adoption versus potentially limiting innovations in proprietary solutions, basically.
Okay, yeah, it's a big question, and I'll try and break it down as much as possible. So with modeling, we've always modeled. So even since WCDMA, for testing, a company like ours, we model early, and we use stochastic statistical channel models. But what we're seeing now is people want more fidelity, higher fidelity, and this is where things like AI is coming in to turbocharge another concept, ray tracing, so that you can get finer detail of your channel. And it's not just a mathematical stochastic model anymore, but now based on the objects that are in the area the reflections, the refractions, and you put that all into those rays and use them to create channels. Now, with higher fidelity channels, you can now evaluate your systems better, and the approximations that we had before will be reduced. And hopefully, the aim is that when you go into the field, you have tested as close as possible to what you want to do, and that will drive innovation that way, because you can do a lot more things earlier using technologies like ray tracing and AI to enhance your modeling.
Thank you. And Malachy, it's been some time since we heard your voice. So where do you see the most critical innovation happening right now in the ground segment? And how is it influencing the broader space value chain, from system performances and, service delivery?
I'm allowed to say phased arrays.
You are?
I think, well, there is phased arrays, but you tie in. There's a lot of sort of the software. We hear software defined a lot, sort of getting mentioned. So that's given a lot more flexibility. We're in a very sort of two things: fast moving, in terms of where's the industry going to go. We've lived in the satcoms and terrestrial have lived as separate lives, I think, and now that's all coming together, which is when nobody really knows how that's going to end up. As the terrestrial is probably bigger than the satcom industry, so is it just going to take us out on all that side of things? So so I think certainly the software side of things is opening up a lot of options and business models as well. So where different people could bring in sort of new services as part of that. But just thinking about testing, one of the downsides about software defined is that you can change it. So you may go along, validate it, do all your testing, and then somebody does a feature update, and like a bug. If we have a bug, for example, in our antennas, that could mean that we are jamming other satellites.
Yes.
If we do that wrong. So there's, I think there's a lot of value in there, but we need to be careful of the risk that comes with it as well.
And Tudor, with satellite constellations innovating all the time, we know we heard about many innovations on that front, and network architectures also evolving quite quickly. From a hardware and RF system perspective, what's driving your innovation? What can you innovate?
As I said before, I think it's driven by the desire for high volume, for a start. When we're seeing that wheel pull for high volume, that's a massive shift for most of us. We're in the space segment, and even the ground segment, we're used to doing things in ones or tens of, not in hundreds or thousands of, and that's a massive change. And it changes your whole mindset about how you do it. You have to now think not only about, can I do it technically, but can I actually scale it to volume? How do I do it repeatedly? Doing things once or 5 times is okay at high frequency. Doing it 1,000 times is much harder. So that changes the way you think about things in terms of the problem set. And then the other one is high bandwidth. We're constantly driving for more data. And we're seeing that, you said, Cabe and yourself, but there's already people pushing beyond that. QV has become very interesting in terms of the spectrum, and that's got 5 gigahertz as a bandwidth. And again, E-band, I think people thought that was impossible before, but SpaceX are doing it already. They grabbed hold of that, and they already have ground to satellite links working at E-band, 81 to 86 gigahertz, delivering massive data rates. So that's really driven a whole new product set for us, really.
And how do you actually balance between the technical excellence with the commercial scalability? It's a tough one to
it is a tough
balance.
one to crack, and sometimes you have to convince engineers that the optimum technical solution isn't the best commercial solution. That's a conversation you have to have regularly and push them back and say, that is definitely the best way to do it, but that's not the commercially minded one that's going to win the business. So that's a balance. I think we're lucky at Filtronic. We come from a commercial comms background. That's all about margin. The margin's very slim. It's all about cost. So we have that sort of cost engineering mindset from the very start. Everything we do comes from that baseline up and say, well, what's the minimum we need to do actually to get the quality standard out? And then we got that. So we're in a good place, I think, to come at it from the opposite way, I think, from where most people are coming from it in the space market, who are coming from a pure quality, everything has to work, everything is super critical. We've got to flip that on its head now, I think.
it's difficult to translate innovation into the real world, I guess. It's often where the biggest challenges arise. So, you know, in a complex world, and what would be the key obstacles for you, Malachy? I mean, when you have going from
well, I mean,
R&D to the full service, you know, they often call it the valley of death between the innovation and commercial success.
I've been involved in a number of startups and different technologies, and the valley of death is just a lot of the time where I've lived. And I think at the start, so, you know, there's, you know, you got to remember you've got to do the bit before the valley of death. So, you know, it's getting that early adopters. So while you talk about technology, you still need some of those early adopters or anchor customers, or, you know, whatever you want to call them. So they're key, because to get across the valley, you've got a different customer. So, in fact, you know, your point about being able to, you know, manufacturability, you know, reliability becomes more, because you're starting to move to a stage where it's higher volume. The you know, the risks of failure are much higher, you know, for your customer if they buy that new technology. So, you know, you're having to, you know, it's, you know, rather than you know, showing somebody a demo for a few minutes, you know, how do you show somebody that you've got a new technology that's reliable, hits the commercial points, and it's repeatable, etc. So, and also interoperability with their legacy systems as well. You have to give them that migration path as well, unless you're lucky enough into something brand new, but you still need to be able to plug in. So, you know, we talk about NTN, you know, we're trying to, as a SATCOMs world, we're trying to get terrestrial people to use satellites, but actually we need to plug into the 3GPP requirements, and so there's an education there. So if you like, we're in the SATCOMs is in the valley of death of terrestrial comms, you know. So we're trying to get the terrestrial world to believe satellites could bring them you know, the main street. That's the other side of the valley. So, yeah, so it's reliability, repeatability, commercial.
And Obi, speaking of, you know, some of the key hurdles, what would they be for you? Because you kind of put the two worlds together, and you have to, you know, look at many different aspects. So would it be something on regulatory or standard release? Interoperability challenges, or any other things that we sort of don't even think about at this moment?
Yeah, so the way I always put it is almost like how Malachy put it just now, is 4.5 years ago, I knew nothing about satellites. It was a pure terrestrial play for us. And 3GPP came along, and we had to learn it really quickly, right? Very, very quickly. And of course, we're not saying we're there yet. And that's where this collaboration comes in. So interoperability, as you're saying, is one of them, because even in one of the projects we did there, showed the press release, you could see about 6 different companies coming together, bringing different skills. And the meetings were very insightful, because somebody brings the idea from here, another person brings actually this is what happens here, and then you have to put all of that together to form a coherent system. So interoperability is one big one, both in terms of people as well as the technology, right? People need to learn each other's thing as much as possible so that you can, you know, make sense of the whole system, as well as putting the pieces of that technology together. Of course, the other major one is hurdle is always money, right? Finance. Without it, nobody can get these things off the ground, because these are very complex and expensive systems to build, right? So terrestrial alone was expensive, satellite alone was expensive. You put the two of them together, and you even get a doubly expensive system. Yeah.
Well, they say innovation rarely happens in isolation, so obviously collaboration is quite important and major driver. But you mentioned collaboration and partnerships, so are you talking about with SMEs or academia or governments, or what kind of partnerships would actually drive this business forward?
So, practical example, SUTD Academia, University of Technology in Singapore, working with JSAT, a satellite company, working with VIAVI, a test and measurement company, working with an antenna company that came into TMY Tech, I think from Taiwan. Different locations, all coming together to build one test system to make that end-to-end call work. So it's across the board, both in academia and in industry as well.
Malachy?
Yeah, no, I always say you can never do everything all yourself. I mean, that's what you sort of got to understand. So it is definitely working with partners, whether that's your your supply chain. You sort of need a partner with them, so they bring capability to you. But it's also, if you want to do larger projects, it is exactly what you said there. It's working with other people that it's the 1 + 1 = kind of 4 scenario. And you bring some sort of higher value in there. In terms of academia, I mean, there's two sides to that. One's kind of research and new things in there, but talent and skills as well. Sort of working with them. So what I find is if you're working on new technologies, trying to influence some of the courses and sort of what they're teaching in them courses as well. Sort of sometimes it's when they teach them, because some subjects can sort of happen at the end of, say, an undergraduate. But if you can get it earlier in the course in the second year, you can find that you could have graduates coming out that's more relevant to what you're doing as well.
Mark was talking about that earlier today, the talent that, there is there, but it's actually how to get the best out of them and how to prepare them for the industry. So it's
I think the difficulty with talent is if things are moving really fast. So if things are moving faster than 4 years, 4 years in Scotland, 3 years in the UK or in England, for a university degree, you can get talent coming out that's actually, oh no, that's old stuff you were been getting taught, how do you get the new things? And there's probably lots of people sitting in this room that went to university and the stuff you learned there is so out of date that, it's just changed. The stuff we're doing now wasn't even around to teach in those days. So, that just shows you how the universities themselves have to actually keep up and be able to react quickly.
My first computer had 48 kilobits.
Okay. 48 times what mine had.
So, Tudor, we spoke about collaboration, and do you see more demand in different models, business models across Europe? Do you cooperate a lot with the?
We do, and I'd echo what you said about supply chain partnerships. I've talked about before, and how important that is to actually work with the supply chain to upskill them, to get them to the place where they can support you. You have to work with them. It's not a supply arrangement, it's more than that. Academic, we talked about, and we do that a lot as well, and particularly for future road mapping, so we can do a limited amount of R&D within the company, and it has to be pretty close to market, really, and has to turn into money fairly quickly to satisfy the investors in the board. But you still need to keep an eye on the 5-year, 10-year timeline, and the best way to do it really is to work with universities, and it has a dual work. It helps them learn. It gives you potential future skill sets as well, so it has a real good synergy, I think, working with it. The other type of partnership we probably haven't talked about is one like SpaceX, where we're partnering and they're dragging innovation because they want it so quickly that we've had to develop things much faster than we ever would have done before. We've had to really react to that pull from a partner, and they're challenging us, really, as a company to say, what can you do? How fast can you do it? Can you do better? And that really drives the innovation curve really fast.
And what do you think, I mean, in your opinion, what's still underdeveloped or unexplored area, from the innovation perspective? Is there something that we are kind of lagging behind in particular?
I'm trying to think of a good answer to this one. Everyone else has a good answer, but the difficulties we have maybe facing collaboration can be difficult, I think, in terms of funding, and when you have funding that's driven from government and you collaborate with universities, for example, IP quite often becomes a bit of an issue. I don't know if you had that problem as well, but universities tend to like to keep IP and companies want to use IP, and there's a disconnect there somewhere. So I think there are some challenges to overcome in that innovation space so we can actually collaborate better together, because I think quite often universities hold on to IP and then do nothing with it. And frankly, it would be better if we just shared that knowledge and let companies like ours actually sell the products at the end. So I think there's probably some things to be solved there.
probably less sort of technical, I think, for the UK, even at European level as well, is how do you get that investment as well? We talked about, where's most of the satellites coming from? It's not here, it's not Europe. Is the ground segment actually, how much is actually coming out of the UK as well? So and it's always a challenge in getting that investment. How do you scale big? Think global. It's not this, especially the space industry. You can't sort of think at a national level. It is a global there, but it does take money for and the UK does have a lot of SMEs. So how can they sort of work on a global basis? But yeah, just the funding, the investment. Can we get the comparable levels here?
I think you just answered my next question, because I was going to ask, what would you change? How do you think it would get better? And obviously investment is what covers most of that as an answer, I guess.
Yes, I think it is. I think also, sort of be ambitious as companies. Sort of don't, like I said, don't think national. Think global.
Think big.
Sort of, and look at the world as a market, and assess where's the best, most accessible ones. Prioritize how you're going to sort of grow that out, and look for those partnerships around the world, and whether that's customers right through to partners in the supply chain. That's the whole spectrum.
Before we turn to the room, is there any advice you would give to a startup these days, and looking how to break into the space value chain? Any words of wisdom?
Stay focused, I guess. Don't try to do everything you can do, especially when you're small. Sort of focus, understand sort of what are you bringing. Understand the market. Don't sort of come out with a kind of new bit of technology. Just because it's new and shiny, it doesn't mean people are going to buy it. Always, as a small business, look at what the problems are. Look at what people are having pain with. And then sort of work it backwards to the technology, and hopefully that might align with something that you can bring to the table. So find the pain point. Well, find a pain point that people pay money for, and so go back to yourself.
Yeah. It helps.
Yes, and do that, and be tenacious about your belief.
Anything to add?
I guess. That is exactly it. You have to focus, eyes on the prize, know what you're going after, understand the market, understand the value that you add in. That's critical, and don't get distracted. I think in terms of support, UK Space Agency are very good, as are ESA. They're slightly painful to work with, frankly, and timescales are long, but they are very supportive. When you get to the end of that, they will support you. They will introduce you to other companies, and they will fund you quite heavily once you get successful. So they will help support.
And the other one is, don't be afraid to ask for help.
Absolutely.
Go and talk to people, because it's surprising. There's even here there's a lot of expertise, and I'm sure if anybody asks, sort of like, oh, I'm not too sure about something, people are willing to help.
Again, collaboration.
Yeah, absolutely.
Yeah, don't be afraid to ask.
Obi, anything to add to this before
I
we
think
turn to the room?
mostly. I think the ambition one is really key. I think that is essential to making it happen, and. Like I was saying earlier, just making sure you're able to evaluate your ideas properly as well, right, along the way.
Absolutely.
You don't want to.
If you're going to fail fast.
Exactly.
That's
You don't want to do it at the end.
Thank you. Richard, any questions from the room?
You
Lance Russell
should have
again.
your own mic.
Data science dynamics.
You should have just been here.
Of course, he was approaching anyway. So Tudor, I'd love to know if you could speculate around what it is that made you the right fit for SpaceX to come and collaborate. Do you think that there is a sort of set of tick boxes that you might have met? Was it all about the technology? Was it about how you packaged it? I'd love to hear your thoughts, beyond Filtronic. What would someone really need to do in this industry to work with them instead of trying to work out how to outdo them?
So I think you're asking why they came to us. I think it is technology driven, really. I think there are very few people in the world doing what we're doing at the frequencies we're doing. So I guess we were lucky in that regard, if you like, to have that very niche technology they really wanted. We'd explored that with others in that sort of community, in the HAPS community in the US. And I think a lot of those engineers ended up at SpaceX and other companies in that area who basically said, these are the guys who know what they're doing in that domain. I mean, we have a very strong engineering team with very clear focus on that very high millimeter stuff, but also the ability to scale product. Like I said, they can develop products very quickly. And we've shown that through other stuff we've done with other companies, and that news spreads as well. The ability to take a concept and turn it into a design and even scale to production in 6 months or 9 months is something that not many can do. And we were that kind of fit. They wanted someone who could react quickly. They needed someone with the right technology, but who could actually turn things around and actually do things in a really fast manner, because they don't wait. They'll cut you off. You know, if you can't do it in 6 months, then they'll go somewhere else.
Any other questions? No?
No, not even Renato? Well, from my side, just a very quick yes or no question for the end. Do you think at the current pace of innovation in the space sector, is it fast enough to meet future commercial and societal demands? So, yes or no?
Yes.
Yes.
I can't put it yes or no. I'll say no in Europe.
Ah, you spoiled it.
Okay.
Okay.
That's the challenge of putting down. I think no in Europe. I think
So just
faster.
in Europe?
Yeah, I think it's faster in some other regions, yeah.
Okay, well, thank you very much. It's clear that the innovation in the sector is not just about breakthrough and technologies, but also how do we implement it, work together, stay adaptable, and scale in this very rapid changing global landscape. So thank you again. Thank you for your time. Thank you, audience. And enjoy the rest of the program.
Thank you.